project is related to Einstein constraint equations, but maybe in a little bit more general context than the vacuum case. It's this is joint work. In fact, this is part of a program involving some researchers. Rodrigo Avalos, he's going to talk tomorrow, I guess. Paul Laurent from Paris and Nicolas Marc, a former student by Paul, and are pursuing some scientific goals with this project. Maybe you'll be clearer in the Rodrigo's talk tomorrow. So the context here, the setting is considering some remaining Lorentzian manifold V. So V is our space-time. I'm supposing for the beginning that V is globally hyperbolic. It's modeling Einstein field equations in this globally hyperbolic setting. So V can be splitted from the beginning into M, which represents the remaining manifold, M the inverse, Mn, and R, which is the time direction. So that's the splitting that we're considering for now, space and time and directions. And then the G bar represents the Lorentzian metric in the ambient V. So we have here the Einstein equations, the left-hand side, of course, the Einstein tensor, and the right-hand side being this general energy momentum tensor T. So our purpose here is to consider especially the case when T is linked to, say, Maxwell equations, to electromagnetic forms. Let me just present some choices for T. You are more interested in these last two, so you are considering, in fact, during this talk, the case when T is given by some charged fluid, in the sense that you consider here the fluid with these physical properties. M is the mass density for this fluid, P is the pressure, and E is the speed of the particles in this fluid. So we have kind of perfect fluid model, but this fluid is charged in the sense that we are considering some charge density Q, and this charge density in motion generates this two-form F, which corresponds to a mathematical model of the electromagnetic form. Of course, if you split F as well in terms of space and time components, you can read from F both the electric and magnetic fields. So our purpose here is to consider that model of charged fluid in this pervading this universe. So in that for this particular choice, you have the Einstein field equations G, that G equal to T can be read in this first equation in 3. So the first equation corresponds to the right-hand side given by this charged fluid. So you have the TF, T subscript F, given in terms of the electromagnetic form F, and that part corresponds to the density of mass, followed by this component of the energy momentum tensor for this charged fluid. So that's the particular aspect of the Einstein-Maxwell equations we are dealing with. The second and third equation, sorry, these other equations here correspond to the Maxwell equations in that context. You can read also this fourth equation as a kind of local conservation of mass. So this is a consequence, of course, of the fact that both sides of the Einstein equation are divergence free. So you have this physical consequence here of this. In the last equation is the equation of motion of particles in this model, in the sense that the accelerations of these word lines are given by the expression of the Lorentz force on the right-hand side. Of course, if you have no charge density, if you have vacuum, for instance, then you recover the fact that the motions are given by geodesics. So that's the model. We have, of course, the way to express this system in terms of a hyperbolic system of equations. It's possible to write 3 in local coordinates and restore the aspect of these equations in terms of some hyperbolic system of equations. So we can, for instance, consider that this dynamical form of writing down the equations, the Einstein field equations, in terms of the second derivative of the ambient metric, in the sense that you are just making some normal presentation of this hyperbolic system in terms of the acceleration of the ambient metric given by the Laplacian of the metric, so it's not the Lambertian, but the Laplacian of the metric, plus some terms which corresponds to nonlinearities coming from the interaction of the metric with itself, the metric with the material fields, etc. So these nonlinearities will be expressed later on in terms of the constraint equations. Well, given this second order equation, this dynamic equation, you have to prescribe the initial data in order to have some kind of initial value formulation from these field equations. This initial data can be given in terms of the initial value of the metric, the ambient metric, and the first derivative of this. One possible way to interpret this initial data is to see that in this space-time view, you can pick up some initial remaining manifold M. So M is that, say, t equal to 0 configuration of this space-time. So you have some remaining manifold M. That's the initial, say, geometric model you have. In M, you have, of course, the induced metric for the ambient. So V is, again, the space-time with the Lorentzian metric. So you can consider the metric induced on M by the natural immersion of M into V, which is that I, which is here. So that's the induced metric. And K is, for the time being, K is the extrinsic curvature, is the second fundamental form of M into V. So this pair is given by the immersion of M into V. And you can see that G could be read as the initial data, the initial, say, value of the ambient metric. And kappa could be considered as the first derivative of this metric. So these two data here, the value of G into t equal to 0, and the first derivative of t at t equal to 0, this data can be read in terms of the induced metric of M in the second fundamental form of M. The fact that the first derivative is connected with the second fundamental form is expressed by this equation here. We have this classical expression in terms of the first derivative of the metric and the second fundamental form. Okay, so the point is that you have to invert the terms here, in the sense that in order to formulate this quotient problem to these Einstein field equations, we start with some abstract remaining manifold, and so M is no longer embedded into some spacetime. Now we have to construct this spacetime. We have to obtain this immersion at the same time to construct the immersion of M into this spacetime V with this Lorentzian metric G bar. So the only thing you have now is the triple M, J, and K, G and K. So you have the remaining manifold M with this induced metric G and this formal second fundamental form. So K is, from now on, K is just some bilinear form, bilinear symmetric form, pointwisely defined on M. So K is a tensor, a formal tensor. And of course, it's hopeless to try to find some immersion for any pair of data G and K. You have to assume that G and K satisfy some compatibility equations. And these compatibility equations are obtained by the Gauss-Kodadzi classical equations in the hypersurface theory in Riemannian geometry. So G and K satisfy this compatibility Gauss-Kodadzi equations, and you have to combine those equations, which are classical in geometry, with the Einstein field equations. So combining both set of equations, at least when you have the simplified case of the vacuum space time, in that case, the compatibility equations of Gauss-Kodadzi coupled with the Einstein equations give us this system in 4. 4 is the so-called constraint equations. The first equation is the Hamiltonian constraint, which corresponds to some sort of Hamiltonian density for general relativity. And the second equation comes from the Kodadzi equation and expressed as the momentum constraint. So we have the Hamiltonian constraint and the momentum constraint. Both have to be faced if you want to obtain this isometric immersion I. So the real purpose is to focus our attention in this system 4, And the classical result due to Shokebura and the following the work by Lishnerovich and the classical one of the classical results by Shokebura is that one. So if you start with some remaining manifold MG in some Sobolev class, and if you prescribe this, if you just pick up this data G and K as being data that satisfy the constraint equations, then it's possible to solve the dynamical equation, the second order derivative of the metric, say, or the Einstein-field equations, the set of dynamic equations in the Einstein-field equations. You can solve them if the initial data satisfy the constraint equations. That's the classical result in the context, for instance, of compact remaining manifolds and that particular choices of Sobolev spaces. You can obtain regularity results, etc. But for the time being, let us take this as a model of the existence result for this sort of problem. Okay, the amazing fact is that if you start with data that satisfy the constraint equations, then the mere evolution of these data in the spacetime permits to obtain at each slice, at each time, copies of M, and the induced metric again in the second order form satisfy for each time the constraint equations too. So starting with data that satisfy constraint equations, those equations are, say, preserved along the evolution, the dynamic evolution of the metric in this spacetime. That's the key results you have in mind in order to pursue the aim of obtaining solutions for the non-vacuum case in non-compact settings. Okay, so the purpose here is to see how can you manage to solve these constant equations with this non-trivial right-hand side. So the right-hand side is given by information coming from the Einstein, for the energy momentum tensor. So some sort of components of this energy momentum tensor appear in this right-hand side. In our particular case, this T, this energy momentum tensor, is given by that particular choice of the charged fluid. Well, that's the kind of system you have in mind, but you have to add another equation here that in some sort prescribes also the electromagnetic field from the charge density in this fluid. So that's the full system. 6 is the full system when you have the first two constraint equations in the classical setting, but you have epsilon j determined by some particular choice of the matter in this universe. In our case, as I said, is this charged fluid, and this charged fluid has some charge density Q, which is in this right hand side, and this Q determines the electric field. The electric field is one of the aspects of the electromagnetic form. So this sort of Poisson equation here in 6 is the element that was lacking in the first two equations. So now we have the full system of equations prescribing all the geometric physical information in the initial surface M. So from now on, you only have M, which is that abstract remaining manifold with the metric G, the formal second fundamental form K, and this charge density, which generates all the information in E, J, and epsilon. The idea now is to follow the steps by Lishnerovich, Shokebura, and try to represent this system 6 in terms of, say, PDEs. To do that, you consider some particular gauge for this initial data. For instance, you assume that M, the initial manifold, which is Riemannian, has some background Riemannian metric gamma. So gamma is the fixed metric in this initial surface M. So gamma is that initial background metric. So you deform gamma in terms of conformal diffeomorphisms, or in fact conformal changes of metric as expressed in this first equation 7. So you want to find this metric G that satisfies the compatibility equations, the constant equations, but G is given as a conformal deformation of gamma. and you choose the particular aspect of this conformal deformation in order to link this problem with the Amable problem. So phi is the conformal factor you want to find. Concerning the second formal fundamental form, you have the trace part of the second fundamental form, which is the curvature. The mean curvature is expressed here by tau, following the classical notation. And the traceless part of the second fundamental form is given by this kappa tilde. This kappa this k tilde, sorry, is given in terms of two orthogonal factors here. One of the factors is free, so you can freely prescribe this component u of the traceless part of the second fundamental form, but there is one term which is given in terms of some PDE. So x is not free. X is determined by some equation I will show you in a moment. So u is free, tau is free, gamma is free. You can freely prescribe the initial background metric in M. You can assign some particular free choice of mean curvature, and you can also freely choose this U. The other terms are determined by PDEs, as I want to show in a moment. This operator is important because this operator is kind of a conformal version of the Lie derivative, and the kernel of this operator will be very important to consider the invertibility of the equations, the operators you have to consider in a moment. That's the operator whose kernel is formed by the conformal fields in the ambient. Okay, so having these choices in mind, you can write the Hamiltonian equation in terms of this PDE. So the Hamiltonian constraint is given in terms of the Laplacian of the conformal factor, the Laplacian taken with respect with the background metric in M. So the Laplacian of phi is given by some nonlinear terms involving. The first one is simple, but the other ones involve the prescribed data. But the first one is the scalar curvature of the initial background metric in M. This is the traceless part of the second fundamental form, which is formal up to now. Tau is the mean curvature. In both equations, you have the influence of the mean curvature. And epsilon and j corresponds to the mass, to the density, and to the current given by the physical fields. And phi is the conformal factor. So you have some expressions which involve powers of phi of the conformal factor and some coefficients that involve both the mean curvature and the presence of these matter fields in the ambient. For instance, if you assume in this last equation here, which is the momentum constant equation, if you assume that our initial surface has formal constant mean curvature, and if you assume that there is no matter fields in this ambient, if you have just the vacuum case in mind, so this coefficient is 0, and you are left with some Laplacian of x equal to 0. So it's easier to solve the second equation in this say more specific case. And this equation, when you consider constant mean curvature in vacuum, this equation is decoupled from the first one. So it's possible to decouple this system and to solve equation by equation separately. And it's not trivial, in fact, but it's easier than the most, say, complex situation when you consider not necessarily constant mean curvature initial surfaces, and you consider to the case of non-vacuum, say, spacetimes. Well, let me just insist with that you have some free data in our setting. You can freely prescribe the initial metric in M, the mean curvature, the formal mean curvature in M, this free part of the second fundamental form U, and the two last terms here that corresponds to the matter fields in this M, the restriction of these matter fields to M, which is the initial surface. So that's the three terms you have. Let me just advance a little bit to the last the last way to present this system you have to solve. So that's the system that corresponds to Einstein-Maxwell coupled equations in this initial value formulation. The first equation is again the Hamiltonian Constraint equation formulated in terms of these factors. So start with gamma. You have to transform gamma conformally to the correct, say, metric G, the metric we're going to find in the end, which satisfies the constraint equations. So that's the expression of the Hamiltonian constraint in terms of some PDE. So the leading part is the Laplacian, and I have some linear part here, and it's very important to have some sign to this scalar curvature of the initial metric. So that's the linear part, but the other remaining terms are very nonlinear. They have this more or less complicated expression in terms of powers of phi. But the point is that the coefficients, again, involve all of this interaction with the metric, with the second fundamental form, but especially with the matter fields. So there's no way to, again, to decouple the equations in this 11 system here. The second equation corresponds to the momentum constraint equation. So again, you want to determine this non-free part of the second fundamental form. But this, again, can be formulated in terms of some Laplacian, which is now a vector Laplacian. But the right-hand side, again, depends on the mean curvature. It depends on these guys, omega 1 and omega 2, and of course, omega 1, omega 2, as well as epsilon 1, epsilon 2. All of these coefficients depend on these physical properties of this fluid. So you have the density of mass, the density of charge, the speed of the particles in this fluid, etc. So there is no way to erase these contributions unless you are assuming that you are back to the vacuum case. So either you consider no-vacuum case or you have some decoupled system. There is no way to uncouple this in this more physical, meaningful situation. And the last equation on 11 is basically how to start with the charge density and to determine one of the components of the electromagnetic potential. F is some sort of potential for the electromagnetic field. F generates in some way the electromagnetic field. In fact, to be correct, F is one of the components of this guy, because F is the exact component of the electric field, but you also have some free component here by this, say, Hodge-Dehaene or Helmholtz decomposition. So theta is free too. Well, so that's the system. Important fact here is that the left-hand side is composed by Laplacians. So we have Laplacians in some fiber bundle, say, on M. But the right-hand side, which is formed by these nonlinear components here, these nonlinear terms, the right-hand side is a very complicated expression. So the idea here is to find a balance between obtain some inverse of these Laplacians. So you have some sort of operator that starts the operator. The nonlinear operator here is we start with phi, x, and f, and you have this right-hand side. So the operator is in that way. The idea is to try to invert this operator, try to find an inverse for these Laplacians. But this inverse has to be constructed in such a way that the right-hand side could be controlled in such a way that you can find some solution for this system. So at the same time, you have to control the norms in some Sobolev appropriate space. You have to control the norms of the right-hand sides and to make it into some Hilbert spaces that are chosen in such a way that the inverse of these operators work well. So you have to guarantee at the same time invertibility of the operators and the control of the right-hand sides, which are very heavy terms due to the nonlinearities, and the interactions between these three equations. Okay, in order to have, let me just phrase the problem in that way. So you have these choices of Sobolev spaces to model this problem. So the system 11 can be um, um, say, put in this way. So you have this operator between sublevel spaces. In that case, M, again, M is that abstract remaining manifold. We're assuming since the beginning that M is either compact or M is complete, non-compact, but asymptotic in the sense that outside some compact regions, each end of M is asymptotic Euclidean. The metric in each end of M is very close, say, to Euclidean metric, and the metric in M in each end decays at a certain rate to the Euclidean metric. So this rate of decay permits to choose also the rate of decay of the subleft norms of tensors. Each tensor, you consider the metric, the second fundamental form, the scalar fields, you consider each of these tensor fields. You are assuming that these tensor fields belong to some Hilbert spaces whose norm decays also in these ends of this space. So at the same time, you are assuming that M has this decaying metric in the sense that the metric is closer and closer to the Euclidean metric in each end, at each end. And at the same time, you're assuming that the sublevel spaces have weights. So it's not the classical notion of sublevel space for compact manifolds, but the weighted version of it. Just to make this clear, have this assumption concerning the sublevel spaces that the sublevel norms decay with a certain rate that depends on the distance from a fixed point in M. So that's the assumption you have in order to formulate this operator view of the system 11. Okay, so in terms of this operator, you start with, say, this u, which is some scalar function, and you have this modified operator, which corresponds to taking the scalar Laplacian, but shifting this operator by some negative potential. And you have the scalar, the vectorial, Laplacian that takes x and computes this conformal version of the Laplacian for the vector fields. So that's the operator you have, and you can guarantee that if you choose the weights in the sublevel spaces according to the decay of the metric in terms of the rate of approximation of the metric to the Euclidean one, if you choose the weights in that suitable way, then you can see that both operators are isomorphisms between these two sublevel spaces. So it's possible to obtain inverted operators here. So that means that you can invert both Laplacians essentially. Besides that, you also have some guarantee of the maximum principle. So both results are key steps for producing the solution of the system 11, which is again the system that encodes the Hamiltonian constraint, the momentum constraint in this equation, the last equation that corresponds to this Poisson type equation that generates, say, the electromagnetic field. Okay, so let me just go ahead a little bit. The problem is that one, 17. In some sense, you start with this weighted Hilbert spaces. You have this triple, which is, again, the conformal factor, phi, the electric potential F, and this non-free part of the second fundamental form. You start with this, you apply the Laplacians for each one of these terms, and you get that horrible right-hand sides in each equation in 11. So this is this right-hand side in 17. This triple here is basically that very nonlinear and coupled expressions that corresponds to the right-hand sides of which one of the equations in 11. So this right-hand side, you can write in a simple way like this F, this capital F of psi. Psi is the triple. We want to find the triple phi, F, and X. We have to find the conformal factor, the electric potential, and the non-free part of the second fundamental form. So psi is the unknown we have here. So F is applied to this guy. So this is a very nonlinear operator. So 18 here, the right-hand side is nonlinear. and P corresponds to this sequence of Laplacians here. So the purpose is to invert P, so to obtain psi as a kind of, it's exactly a fixed point of this operator P minus 1 F. The idea is exactly to invert P and to control the norm of F. I have to control the norm of F, this non in such a way that the inverse operator can act on this right-hand side here. Well, we start with some particular initial approximation of psi. Of course, you have to obtain some kind of contraction argument here to obtain some fixed point using some contraction arguments for these operators. So the first approximation is that psi is 0, say, and then have to solve this equation for this first approximation, psi naught, and then to obtain the psi 1 as the second step in this iteration. So, and start this process again and try to control at the same time the norm of the right-hand side and the range of this right-hand side in such a way that you can apply the inverse of P to this right-hand side. It's a trade-off, because at the same time, if you have some invertibility result for P, you have to do this in the same sort of spaces when you can get the control of the norms of F. It's hard to balance these two things at the same time. Well, that's the general result that states that that thing is possible, in the sense that you can at the same time control the size of the nonlinearities in terms of some weighted Sobolev norms. So the right choices of the weights, the right choices of norms permit to control F, and that control is made in a space, in a Sobolev space, for which you can obtain the inverse of the linear operator Laplacian of F, Laplacian of psi, Laplacian of y. Remembering that phi is the conformal factor, F is the electric potential, and y here is that non-free part of the second fundamental form. So that's the result. That's the way to express the result in terms of this functional perspective here as a map between weighted Sobolev spaces in this asymptotic Euclidean manifold. But the master assumption here, the key point, is to assume that you can find sub and super solutions for the Lishnerovich equation. So the most complicated equation, which is the first one, to find the conformal factor. This equation corresponds to the Hamiltonian constraint, and we are assuming here that you have sub-solutions and super-solutions for this equation. Besides that these sub and super solutions are strong in the sense that at each iteration in this fixed point argument, at each iteration, you find approximations for this conformal factor that lie always between the sub and super solutions, in the sense that at the same time the sub and super solutions are not so far each other, in the sense that they are not outside the ball we are considering these weighted Sobolev spaces, but they are separated enough to keep all of the interactions of this conformal factor inside them. So it's a very delicate point in the construction to find these robust, these strong sub and super solutions. You are, of course, mimicking the classical approach by Schwarzschild, but since you have the nonlinearities, since you have these possible far from CMC choices for the initial data, it's no guarantee that for the beginning that you have this preservation of the sub solutions at each step of this iteration for getting the fixed points represented by the solution of the problem here, the solution psi. So that can be done if you assume certain specific geometric properties for this initial data. That can be done, but that's the math result, in the sense that whenever we can find these strong super solutions, it's possible to solve the constraint equations in this more general setting of non-vacuum case, non-compact, asymptotic Euclidean manifolds, etc. There is some kernel in this operator P, which is the Laplacians, and to deal with this kernel, you assume that the asymptotic behavior of these super solutions give some harmonic functions in each end. So it's necessary to prescribe the behavior at each end of these super solutions. So at the same time, we have to find these super solutions that are strong to be preserved in these fixed point arguments, and these super solutions are prescribed at infinite. At each end, you have the right behavior of these super solutions. This reflects the fact that our operators are not free from kernel. They have some residual, say, Jacob fields. Well, so that's the main result, but in a certain way it's useless unless you can find say concrete specific contexts when you can obtain these super solutions that are strong and have this asymptotic behavior prescribed. We'll discuss this in a moment, but the only point is to explain a bit the key ideas of these abstract existence results. So you consider that shift of this Hamiltonian operator, so the Laplacian of the scalar conformal factor has to be shifted by some potential A. That shift permits to use the maximum principle, so then you can start producing new and new iterations of these say of this conformal factor. So you start with the subsolution, you plug this subsolution into the right hand side of the operator, you obtain the new say adjusted conformal factor, and then you can start this again and again. But the key point is to guarantee that each one of the approximations phi sub n of this conformal factor lie between these super solutions taken in the first step of this iteration process. You can extract, of course, subsequences of these conformal factors using say the properties of ellipticity of the system. That's the point, to use the right weights in the Sobolev spaces. And you can obtain, due to elliptic estimates, the convergence to some positive conformal factor field at the end. Okay, but as I said, it's important to see if there are some specific situations when you can find in a more explicit way the super solutions. One of the possible settings to do that is to consider initial Riemannian manifolds whose metric gamma is positive, is with respect, I mean, the Yamabe variant of this initial metric gamma in this initial manifold M is positive. This is one of the contexts. So to consider that the Yamabe variant of the initial metric is positive, in that case, you can assume for this existence result that the physical fields are controlled, in the sense that the free part of the second fundamental form, but all of the terms that determine the electromagnetic field, like F, the mass density, that non-exact part of the potential, in the charge density, all of these physical terms in this free part of the second fundamental form, all of the data are sufficiently small, in the sense that they lie into some small ball in these weighted Sobolev spaces. But in this case, we are free to prescribe any mean curvature we want. So it's not necessary to assume that tau, the mean curvature, is small or is constant, is near to be constant, but could be far from being constant. So in that case, under the assumption of the positivity of the Yamabe variant of the initial metric, it's possible to keep tau far from being constant if you assume that the physical fields are not too strong, are not too big in terms of these right choices of the sublevel spaces. In that case, you can find the strong super solutions by hand. It's a kind of process made by hand in each case. So you can find these strong super solutions, and to make that a fixed point abstract argument to work. And the second context, the second setting you can consider here is to assume now that, of course, you no longer have the positivity of the Amab invariant, so that it's not possible, for instance, to make some conformal deformation of the metric to assure that the scalar curvature is positive. But in that case, now you have to assume, besides the fact that the physical fields are sufficiently small, the gradient of the mean curvature is also considered to be sufficiently small. Since it is not possible to assume that the scalar curvature has a positive sign in the regions, eventually when the scalar curvature is negative, then you consider this interplay between the sign of the mean curvature, or the size of the mean curvature, and the scalar curvature. In that case, if you assume that the physical fields are not too big and the gradient of the mean curvature is also not that big, in that case, you also have the possibility of finding out the explicit expressions for super solutions that are stable under these iterations that produce at each step closer and closer approximations to the conformal factor that solves the Lishnerovich equation, solves the Hamiltonian Constraint equations. Both cases extend in many ways the classical results and the more recent results by David Maxwell, Host, and collaborators, in the sense that you are dealing with the same time, as I said several times here, at the same time with a very strongly coupled system of equations in the non-vacuum case, in this non-compact scenario. The purpose with this project was, in fact, to investigate if it's possible to push these techniques up to the limit and have a very strongly coupled system of equations. And one of the aims, Rodrigo is going to talk about this tomorrow, is to analyze the counterpart of the constant equations for instance, fourth order equations. If you consider formulations of GR involving, say, quadratic functionals, like the quadratic scalar curvature, the quadratic Ricci tensor, in the sense that you combine the quadratic functional expressions to give fourth order equations, replacing the classical Einstein-type equations. In that case, it's inevitable to have a strongly coupled system of equations. In that case, fourth order PDEs. And using this sort of exercise I showed you, it's possible to see that the techniques are strong enough to deal with this case of fourth order systems too. So that result was interesting in itself, but it points out to these other possibilities that Rodrigo is going to explore and elucidate a bit more in his talk tomorrow. Just one final comment besides this is that it's possible to redo all of these machinery, all of these calculations to the case when the initial surface, the initial hypersurface M, has compact boundary components. You can see one of these boundary components as being trapped surfaces or even horizons. And then you can also produce some resistance results along the same lines, basically, prescribing the conformal factor and the mean curvature in the second fundamental form in general. But besides that, the behavior of these geometric and physical data among the boundary components. And it's possible to solve them, these sort of, say, Robin boundary conditions along these trapped surfaces that are the connected boundary components of the initial manifold M. The technical trickier part is to find some sort of Helmholtz decomposition for the data along these boundary components. And Rodrigo was made a very huge effort to doing that, but in the end, it's possible to under some assumptions on the behavior, especially the assumption that the boundaries are marginally trapped surfaces. With these assumptions, it's possible to find solutions to Einstein constraint equations in this Einstein-Maxwell coupled system with these boundary conditions too. So that's the end. I thank you very much for your patience and your audience. Thank you so much.